In the last lecture, we spoke about convolutional neural networks, and today we will be continuing our discussion on CNNs. So let's take a look at what we discussed last time. We spoke about the structure of a DNN, and then we talked about how it could be used to recognize different types of images. And so we said that in order to be able to do that, we need to understand how filters work and how convolution works. And we looked at examples of filters which were one-dimensional, and we looked then at two-dimensional filters. And we'll also look at specifically at different examples of how edge filters can be used to detect edges, different types of edges, as in this example. And then we went ahead with our first example in which we were trying to categorize between one of two images. One is being a slanting slope towards downwards and the other one being an upwards. And the idea was to be able to have some kind of probability associated with each one of those two images, and to be able to say whether if y1 is large, then that would imply that this is a downward sloping image. And if y2 is large, then it would be an upward sloping image. So we would compare the values for y1 and y2. So we looked at different types of filters. We looked at the first filter that we looked at was something which was a sort of like somewhat a replica of a downward sloping image. Okay. And we looked at how this would appear, the output would appear if we use that filter. And then we said, what if we used a second filter, which was sort of an upward sloping filter? So you have these two filters. And when we applied a convolution to this operation, to this particular image, image one, we got an output which was relatively stronger as compared to the output from filter number two. Okay. And then we said we could do a max pooling operation, which would simply select the largest values. And if you applied max pooling with a 2x2 filter over here, then you would get an output of 0.5 over here and an output of 0.25. And this is basically saying that y1 is greater than y2. And if y1 is greater than y2, then what is this image predicted to be? It's can be predicted to be a downward sloping image. Okay, because this particular filter is looking at downwards. This filter here is looking at images which are downward sloping. So now let's continue that thought, and let's look at what if we wanted to we applied the same two filters now to a different image, which was the image number two, which is now the upward sloping. Okay, so we're applying the same filters to the upward. So let's do the calculations. And again, I need your help. What would be the result over here, just to remind yourself how convolution is being done? So we applied this filter over here. And what do we get? Well, most of it is going to be a 0 except for these two ones. And then we're going to divide by 4 to get an average over the size of the filter. So this is going to be 0.25. Is that right?
Yes.
And then if you applied this on this over here, it would probably be a 0 and a 0 over here, my guess, and probably a 0.25. Okay. And if you applied this filter over here, then if you applied it over here, this would probably be a 0 and a 0 over here. But when you applied the filter number 2 in this region, in the top right quadrant, then it would come out to be a 2 divided by 4. So it would be a 0.5 over here, and by symmetry, it would be a 0.5. Okay. So I think we did our calculations right. So that's what we're getting when we apply image number 2 to the same two filters. Okay. So now if we go ahead and try to figure out what would happen if we look at the same results. So for example, earlier we said that y1 is greater than y2. And so it was supposed to be a downward sloping image. And in this case, y2 is actually greater than y1. If we apply the max pooling again over here, then y2, which would come out to be 0.5, and this would come out to be 0.25 for y1. So y2 is now greater than y1. So what we're basically saying is that this filter is predicting that there is a higher probability that there is an upward sloping image in this image number 2. Yeah. Okay, so these numbers are not necessarily right now, as I was explaining towards the end of the last lecture, these are not normalized probabilities yet. Okay, they're simply an indication that you can use it as a relative comparison between y1 and y2. Okay, it's quite possible these numbers might come out to be greater than 1. So they're not necessarily absolute probabilities. All they're saying is that if this number here is greater than this, then the probability that it is of type y2 is higher than that of y1. That's all we're saying right now. Okay, because we haven't looked at the normalization issues yet. Okay, so now what we're going to do is we're going to now start training. So let's say that we have a bunch of images, all of them downward sloping, all right? And we apply them to, we apply both F1 and F2 simultaneously to that image, and we look at the output. So this is what we're already familiar with. In addition, what we're going to do is we're going to rearrange the output, and we're going to have what is referred to as a fully connected layer at the end. Okay. So earlier we were simply picking these numbers by saying max pooling, right? Let's forget about max pooling for a while. And what we're going to do now is use a fully connected layer. And we're going to say that now, what is a fully connected layer? It basically means that, remember, these are all the outputs of neurons. Okay. So if you recollect, this was our basic neural network, right? It had inputs and it had some kind of an output. There was some kind of a label over here, and it would calculate the error. This was the training process that we've already discussed. Now we're going to do the same thing over here, and we're going to say that the label over here, the correct, when we're putting in this image and we're giving it lots of these images, in this case they're all identical, but we're training it over time, and we're saying that the correct output over here should be y2, the y2 hat, which is the label, should be 0, because it is not an upward sloping image. Y2 is indicating it's an upward sloping, and y1 is indicating that's a downward. So all of these images are now downward sloping images. So all the y1 hats should be equal to 1, and y2 hat should be 0. Okay, so this is our label data, and this is how we're going to train this. Okay. Now in the output layer, we're saying that this is fully connected. So what that means is that the output over here, there's not just one y, there are two outputs. Okay, there's one output over here, one output over here. So as I said, you can have outputs which are multiple. Okay, so we have two outputs, and this fully connected layer simply means that we're going to rearrange the output. So we have 4 outputs from this filter, we have 4 outputs from this filter. Okay, we're going to stretch them out. We're going to make them linear. How are we going to do this? We're going to put this over here, 0.5, then 0. So we're basically going to go like this. Okay. And so now you have outputs, 4 outputs from each of the filters. So you have a total of 8 outputs. It's going to be arranged serially, linearly. So you have 0.5, 0, 0, 0.5. In this particular example, when image 1 is given, you have 0, 0.25, 0.25, and 0. So far, so good. This is the output that we're getting. Okay. Now we also have the labels. We've got y1 labels and y2 labels. And now we're going to go through the backpropagation algorithm to train the weights. Now, what are the different weights over here? Where are the weights? Are the filters the weights, or are the weights over here? So I've given you a hint over here. You can see that I sort of left this out. But basically what we're saying is that, I think I got onto the wrong page, that's why. So here what we're doing is we're doing the training, and these are essentially the weights that we're trying to train. In the fully connected layer, the output has certain weights. Okay, we in this particular case, we don't have any weights in the back. We just have weights in the output. Okay, and we're going to be training the output weights. And now the question is, as we train this, what do you expect to happen? So we're saying that this output should be 1. So every time this is a small value, or if it's great value, it will be looking for values over here. Okay, because basically every time you see something like this, whenever you're training it, you're looking at these values. When these outputs are high, it implies that this is downward sloping. Okay, so which one of these weights do you think will become strong as you're training it based on image number one? So you've got 8 weights, right? You've got 1, 2, 3, 4, 5, 6, 7, 8. And all of these are being trained, and they're being trained to say that uh, if this value is high, okay, so let's look at 2 examples. Okay, so let's just stick over here because that will give out the answer. So if we simply set training based on image number one, and we're saying that the weights, image number one is image number one whenever these weights are high and these weights are small, and the rest of the weights are small. Okay, all of these weights are relatively small. It's basically these two values over here, the value over here and the value over here. If these two values are large, then basically saying it's a downward sloping image. So of all these weights, of all these links, which weights do you expect to become larger and the other ones to become smaller? Remember in the playground, I showed you that some of the weights become larger and some become smaller, right? So which weights do you think should become, if we number them 1, 2, all the way up till 8, which of these weights do you think will become strong as you're training it based on image number 1? They'll become increase, yes. So they'll become large as opposed to, so maybe closer to 1 as opposed to closer to 0.
Yes, so I think that for Y1, both the 0.5 will increase.
Right, so number 1 and number 4 should become strong, right? So let's say the weights over here will become 1 and the weights over here will become 1. The weights over here will eventually get close to 0. What about these weights over here? So these weights are going to perhaps be opposite right now. Okay, so it's going to sort of say that, do you think that these weights will become 0, but do you think these weights will be as strong as these two weights? They'll be weaker because you can see that it's more strongly dependent on 0.5. Okay, so these might become 0.25 or something like that. Okay, they might become slightly larger. I'm not saying what the actual values will be, but because it is detecting that these two values are there, but basically so let me repeat. Actually, we want Y2 to be 0. Very good. So actually, what should happen? So will these two values become large or not? No, they'll actually go down to 0 because we want to de-emphasize this. We want to make the Y2 is equal to 0. So actually, they will try to make all of these 0. And because these two values are 0 already, maybe they'll get some random number because it doesn't really matter what they are. The output is still going to be 0. So the important thing is that these two values will become larger, okay? And these two values will probably become smaller as a result of this training, okay? So, yes, so this is binary classification because right now we only have Y1 and Y2. But if we had Y3 as well, then it would not be binary. Okay. So as you can see, I've shown this over here that these weights will become larger and the rest of them might become very small. Okay. Now let's look at what happens when this image is trained. All right. Image number 2 is trained. And now similarly, we expect that these two weights, which will come out over here, we want Y2 to be equal to 1 over here, right? And we want Y1 to be actually equal to Y1 hat in this case will be 0 and Y2 hat will be equal to 1, right? Because we're saying all of these images are actually these images and they're not this image. So we expect again that these two weights will become large and perhaps these two weights will become small. But I've shown them as large over here because these images might be given simultaneously, right? So you may have one image 1 and then image 2 and image 1 and image 2, and you're giving different labels. So as you continue to train, what you'll see is that these weights will also become large, but at the same time, these weights will also become large. Okay. What it's essentially saying is that y1 is going to be strongly linked with these two positions, and y2 is going to be strongly linked with these two positions. Okay, so every time you see something which is high over here, it will immediately select y1 value to be large, and every time it sees these two values to be large over here, it will make y2 large. Okay, this could happen this could happen, at any given time. For any given image, you're going to expect y1 and y2 to be given to you. Okay, so as a result of this, if you look at after the entire training is done and you enter a particular image, so let's say you enter image number 1, what it's expecting, in this case, what's happening is that y1 is going to come out to be greater than y2, and so it's going to select that this image is of type y1. Okay, and if you enter an image type 2 into the same network, remember both of these networks, this network and this network, are the same. Okay, these are identical, but they're in this instance they're being fed image number 1. In this instance they're being fed image number 2. The output, of course, is different depending on what the image is being given, but the weights have already been trained. Okay, so once the weights are trained, you give it image number 1. The output will, in this case, as you can see, comes out to be y1 is 1 and y2 is coming out to be 0.5. And so it will say that the image is more likely to be of type 1 rather than of type 2. When you enter an image of type 2, it will say that y2 is larger than y1. And so the image is more likely to be of type 2 rather than of type 1. So basically, it's giving you probabilities or some kind of numbers which can be associated with probabilities, and it will tell you what image is more likely. So it's basically doing a classification between two types of images. The original problem of classifying cats and dogs, but now instead of having features, we actually have images. Okay, so this was a very trivial, the most trivial example that one can think of to be able to understand this problem. So now I'm going to go to a slightly more complex example. This is also called a toy example, and I've drawn this from this particular website, the YouTube site. You can look at it later as well if you feel that you want to have a better understanding. I'm going to use this example for the next few minutes. So here is an example, and the idea is to be able to take X's and O's and to be able to classify them. Okay, now these X's and O's are going to be handwritten. So you might have somebody writing an XO like this, somebody might write it like this, somebody might write it like this, somebody might write it like this, right? You want to be able to differentiate between that and a series of O's, and of course, O's can also be written very differently. Somebody might write it like this, somebody might write it like this, and so on. So you could have all kinds of O's been written, and these are handwritten images. So, but you want to be able to get the main features of what is it that differentiates an X from an O. Okay, so now remember that each one of these filters, if you think back over here, each one of these filters was selecting a particular feature in the image, right? This feature was looking at a left-leaning feature. This filter was looking at a right-leaning feature. Okay, and that's how it was able to select between these two images. Now the question here is that that if you have a series of X's and O's, then what kinds of features, what kinds of filters would you need to be able to differentiate between an X and an O? Okay, so if you think about how are you recognizing an X and an O? Okay, what is it about an X which makes all of these images common, and what is it about O's that makes all of these images common? Can you explain that? What's the special feature? What's unique about it? What's your mind looking at? What's it?
Sir,
Yes, online, please answer.
the center of the O is like empty and X center is filled.
Okay, very good. So that's very clear that at the center of the O there's nothing there. At the center of the X there is a cross. Okay, even though the cross may not always look identical, but there are two lines which sort of intersecting. Okay, okay, so that's very good. What else can we say?
Also for the gradient.
Okay.
So, for example, if there are two lines in X, so they have the both lines will have sort of like negative
Right, right. So you're looking for one line which is sort of negative sloping, just like we saw earlier. So you probably need a filter which is looking at a negative slope line, and a filter which is probably looking at a positive, even though it may not always be exactly positive, right? But generally, that's what you're looking in the X. Yeah. Okay, in the trend of coordinates, now remember in the previous case, when we looked at filters, we were not able to look at the trend, unfortunately. That was one of the suggestions given earlier as well. But it's very difficult to look at the trend the way because you're looking at pixels and they're not necessarily anyway, it's a difficult problem. It's a more difficult problem. It's easier just to use a filter and to be able to match the way the image is appearing. Okay, so that's a reasonable thought, but that's not how it works out. That's not. That's more difficult. Let's put it this way. Now look at an O. What kind of filters do you think you need in an O? So you've got the filters. So you got in X, we're looking at three things. We're looking at the center. We're looking for a cross, and then we're looking for a filter which is able to pick the cross. We're looking at a filter which is able to pick these two types. So for an X, how many filters do you think we need to be able to catch an X? Two. Well, here we had two. What about this particular the cross itself? Three. So you need a special filter which looks for a cross, because you see, if you had a line over here like this, is this an X? No, because an X always will have two lines crossing each other. So it will look for a special image which has the two lines crossing each other as well. Okay, so now you're looking for at least three filters which will be able to identify an X. And if those three filters give out strong responses, then we know it's an X. Yeah. Yes. And you remember in deep learning, what happens? The first set of neurons do the simple filtering, and the second layer will actually do exactly what you're suggesting. Is they'll actually combine all of those and I'll say this is what an X looks like. Okay, so that right thought, but that comes in the second layer. So I'm just saying that in the first layer, what kinds of filters would you need? So I'm just looking at the first layer right now.
So can we say that when these techniques of deep learning are built on these principles, as their automatic way of designing principles, but in there we're just giving the first layer inputs, and the layers are automatically constructed.
Yeah, so we're defining how many layers are going to be in the network. So for example, in this network, we're going to say that we're going to use a particular architecture. So here we're going to use one convolutional layer, one ReLU layer, and then another. So this is layer one. Okay. In this toy example, we're going to use another layer two. Okay, just to show you that you can have a deep neural network. In fact, this layer is going to go all the way up till here. It's also going to use a max pooling at the end because we want to make the image a little smaller. Okay, then we're going to have another layer which is going to convolution, ReLU, and pooling. So this is going to be the third layer of the deep neural network. Okay, and then what we're going to do is we're going to use two layers which are referred to as the fully connected layers, which you already saw. Okay, so this is going to be a neural network, a deep neural network with a total of 5 layers. Okay, layer 4 and layer 5. This is an example to illustrate. Okay, so now going back to designing the filters, or we're thinking that if you gave an architecture because in a convolutional neural network, not only do you have to specify, in a fully connected network, how many, what's the depth. So you're deciding, this is going to be your decision. As an architect, you're going to say, do I want to have 4 layers? Do I want to have 5 layers? Or do I want to have 500 layers? Okay. If you have 500 layers, it may be an overkill. And it might take forever to converge, as you saw in the playground. If you overkill it, it doesn't really give you an advantage. But if you can think that, okay, if I'm simply looking for X and O's, then how many filters do I really need? And so the convolutional layer will have to be designed by the architect, and you'll have to decide how many filters you have. You won't have to decide what will be the structure of the filters. You won't say that I'm going to look for an X and an O and so on. All you're going to say is I'm going to design it with so many filters. I'm just going to decide the number and the size of the neural network. Okay. So now let's think about the number of filters you would need to be able to decide on an O. Okay, and think back to the filters that we talked about earlier. If you look at this, for example, or if you look at all of these concepts that we studied earlier, right? Edge detection and so on. So now think about how many filters would you need if you wanted to design to be able to select an O. So what is it about an O that's different about compared to an X? So think about the same questions that I asked you about an X. So somebody's already answered that there is an empty thing in the center. But how do you actually decide what's the center? So you can't really pick the center of an image. It's not very clear. But the lines are clear. Is there an X over here? No, there's no X. Is there a left-leaning line? Yeah, clearly there's a left-leaning line over here, right? In fact, a left-leaning line over here as well. It will be small. Yes, you're absolutely right. So the weight of those left-leaning lines will be stronger in the X and weaker in the O, but there will be some linkage, right? So as you saw earlier, that some of these weights may contribute to a Y1 as well as a Y2. Okay, so the weights for the left-leaning lines will be there for an O. What else would we be looking for? A right-leaning line? There'll also be a right-leaning line. What else is there in an O? There's no intersection. That's clear. But what else is there?
So vertical line.
Exactly. So there are two vertical lines as well. And of course, there are two horizontal lines as well. So essentially, think about an O, it's a combination of all of these. Okay. But remember, in an X, there is none of these lines appear. Okay. So these are sort of unique things about an O, which completely differentiates. These lines over here, the slanting lines also appear in an X. Okay. So, yeah. But let's assume that we're only trying to categorize between one of two categories, either an X or no. We're not looking at pluses, minuses, and all the other characters. And yeah, you're absolutely right. But given, so it's conditional probability again. Remember the probability studies we did. We're saying given that it's either an X and or an O, which one is more likely? So it's a conditional probability. You're only trying to classify between X's and O's. And so I'm going to perhaps give this to you as a homework assignment. I might ask you to create images of your own handwriting with X and O's and try to actually see if your neural network can give you the right probabilities. Okay, see if we can do that. So these lines are not very helpful to be able to differentiate between an X and O. So in the O, we expect that perhaps these probabilities will be stronger. Okay, so the filters which are looking for vertical lines or horizontal lines, they will have a stronger impact on deciding whether it's an O or not. Okay, and in the X, the cross will probably be the strongest value. Okay, because that's something completely unique between an X and O. And these lines may have some weight, okay, but not as much as an X. So this is what we're expecting. And now once it is trained, so let's say we give it, hundreds of images. Okay, we give it all kinds of images with all of these images are given to the input and it's trained. And we're training this whole deep neural network. So can you imagine how many points of training will there be? So will the convolution layer have a training weights? So I'm asking you, how many weights will there be to be trained? So remember, in a single neuron, there were weights, the input weights, right? So over here in the convolution layer, will there be weights to be trained? So if you look at what the convolution layer was basically doing, is that it's taking these filters and now it's actually has to decide what the filters are going to look like. Okay, so now these filters themselves are actually have to be designed. The ANN through the backpropagation algorithm is actually going to decide what should be the right filters, okay? Because we're not going to hand design the filters. So it has to now not only decide what the filter should be, it should also decide at some point the output weights, okay? So if you think about this, where are the training weights going to be? In over here, all the filters will have to be, the weights of the filters will have to be decided through backpropagation. In ReLU, what is ReLU doing? Remember, it's simply saying it's a maximum of 0 or X. So there's no weight over there. Okay, it's just a function. So there's no training involved over here. Again, in the convolutional layer, sorry. Yeah, it's simply taking the input and it's a fixed function. Okay. In the convolution, again, over here, there'll be weights. The filters, all the filters will have to be trained. Isn't a fully connected output layer here yet? No, it's not here yet. Okay, that comes at the end. So we're just training the filters here. We're training the filters here. Again, we're training the pooling. Is there anything to be trained over here? So let's say we say that it's a 2x2 pooling, and we're doing a stride of 2. So it's moving. So it's all fixed. Okay. So there's no training over here.
Sir, I have a question. How many layers are going from convolution to ReLU?
How many? So all of the output will be individually. So we'll see an example of that. Each one of those neurons will have to be go through a ReLU.
So for example, if you have a 9 by 9 grid, there will be 81.
Yeah. There'll be 81 functions applied. So each one of those values will be either chopped to 0 or will be taken as they are. Okay. So here you have the pooling. Then again, you have convolution. So there'll be training over here, no training here, no training here. What about the fully connected layers? Do you think there's going to be training over here? Yes, that is very important, right? We said that this is the fully connected layer. It has to figure out which of those weights to be associated with which one of those two outputs. Okay. So this has to be trained. In this example, they're actually using 2 fully connected layers. Sometimes that,
So why are they using so many layers?
Why are they using so many layers? Very good question. Let's go back and think about the example that we saw earlier. That was, I think, in the previous slide. No, it's over here. So if you look at this, or even if you look at the playground example that I showed you, remember that if you had only one layer, were you able to distinguish between the spiral case? You didn't, right? You needed to have deeper layers, because actually what the lower layers do is pick out simple features. As you can see in this particular example, I showed this to you last time, of a face. The first layer is picking out the simplest features. Okay, it doesn't know what a face is yet. It doesn't know what a nose is yet, but it does know what an edge is. Now the second layer, it's a combination. See, all of these are combining this. So when it gets a combination of features which look like this and like this, or like, something like that, it can combine these into a high level feature and can say, this is, a combination of low level features. So the way it's actually recognizing a nose is that maybe it's got a whole bunch of these features. So it's looking for a combination of these. Okay. So when it gets something like this, it says that yes, when all of these features have strong values, it says that this neuron is going to trigger when it sees all of these lower level edges appearing. Okay. And this neuron over here may be associated with an eye. And it's going to say, well, I'm going to look for features which are sort of like very close to each other. And if they're like that in that particular shape, then I'm going to get triggered and I'm going to say that it looks like an eye. Okay. So each one of these neurons is getting triggered or is giving a strong output based on some combination of the inputs. Okay. And that's why you need deeper layers, because, and this was really the magic of deep neural networks. Before deep networks existed, artificial neural networks existed for a long time, but it didn't have the impact. And you can think it's almost a trivial extension. Anybody, it's like a no-brainer. Anybody could have thought of that, but people don't think of everything. You need people like yourselves to be, to be creative and thinking about different ways to be able to design an architecture. So all somebody did was say, well, what if we added taken the input, take the output of the first layer, and we fed it to another layer. Okay. And what happens if we went deeper? So all of a sudden they started realizing that, hey, wait a second, the first layer was able to look at the edges, but the second layer, if you look at the activation map, as they call it, the output of that, we can see that higher combinations of the lower layers are now being used to pick up higher level features. Okay. And if you even go deeper, you can see that this is now in layer 3 is actually picking up even higher level features, and now it's actually able to pick up an entire face. Okay. So that's really the beauty of deep neural networks. That's a combination of lower level features getting, and this is actually how our brain works as well. If you look at an image, and when I look at a table, how do I recognize that it's a table? Okay, and it's not a human being. Why? Because our brain somehow immediately recognizes these edges. It sees sharp edges. So our brain, so in our brain, those neurons which are looking, which know that this is what I understand from a table, they're getting triggered because they're seeing a sharp edge. Okay, so all of these things which are sharp edges, it's automatically recognizing as inanimate objects, and which are probably tables and so on. And then when you're seeing round things and they're looking like a certain thing, we're saying these are probably chairs. And when we're looking at human beings, they have very different features, right? So in our brains, these neurons are getting activated, and this is how they eventually tell us that this is a human being. And then we eventually recognize it, and we say this is our brother, and this is person X, and this is person Y, and so on. Okay. So if we keep going forward, and that answered hopefully the question as to why we have deep layers, and why do we have 3 layers, why not just 1? And so now going forward, now we've already answered the question as to how many filters would you need. Okay, so we're probably saying that we need probably 3 filters over here, and maybe 2 filters over here, basically. And so in total, to be able to differentiate between an X and an O, my guess is 5 filters would be good enough. Okay, so what I can do is I can design a neural network which is going to have 5 sets of filters. So if you can think, this is the input image, I'm going to have a filter here, filter 2, and I'm going to make 5 filters over here, 1, 2, 3, 4, 5. And each one of them could also be fed into deeper layers. But if I'm designing something very simple, I could say that I could have 2 outputs, Y1 and Y2. And I'm going to have a fully connected layer from each one of these. And this is how it's going to look like. And each one of these could be, for example, a 2x2 filter or a 3x3 filter. So if it's 3x3, you have 9 outputs over here, 9 outputs from each one of these. So in the fully connected layer, how many connections would you have for each one of these? So you'd have 3x3 from each filter, and there are a total of 5 filters. So that's 5 times 9, 45. So each one of these would have a total of 45 connections. Each one of the outputs. So Y1 is saying an X, and Y2 is saying an O. Okay. So Y1 would have this neuron over here would basically have total of 45 inputs. Okay, not just 2 inputs as we had before, but it'll have a total of 45 inputs because it will be connecting itself to each one of the outputs of each one of the filters. Okay.
But in the convolution system, we learned that we saw very few outputs, like 2, 3.
So look at convolution. Well, I simplified it when I said that you could have a max pooling, but actually, if at the output of the filter was 4, so if this was a 2x2 filter, it had 4 outputs. Okay, and then so here we had a total of 4 outputs here, and you had 4 over here. So
Okay, sir.
yeah, so there's a small mistake over here. There should also be lines all the way up till here as well. Okay, so you'll have a total of 8. And this will also be connected over here. So you'll have a total of 8. Of course, some of these weights will be very small. But yes, you'll have a total of 8 and 8 inputs connecting to each one of these outputs.
Sir, the convolution layer is different from this fully connected layer. It is connected afterwards.
The convolution, this is the convolution layer. Okay. So this is the convolution layer, and this is the This is the output layer. This over here is the output layer. This is the output of the convolution, and this is the fully connected layer. Okay, so these are the weights associated. So sorry, this entire thing is the convolution layer. Okay, so these are the weights associated with the convolution layer. Okay, now I had picked up those weights, right? I said that we'll design a filter which is like this, but in practice, you don't know what those filters are supposed to look like, right? All you're going to do is give it images, and the filters, this is the magic again of neural networks, that the filters will automatically come into being based on a lot of data. Okay, so after a lot of training, it will automatically come up with filters which make sense. Okay. So now we have these filters. So this is sort of my guess at how, if I were to design a very simple neural network, I would say that I would design it with five filters, each one of them being maybe 3 by 3. Okay, 2 by 2 is too small to detect a slanting line. So 3 by 3 would be good. You could design it bigger as well, 5 by 5 filters as well. You could design it 100 by 100. But as the bigger the filters become, the more computationally complex it becomes. Okay. So now let's look at this example. So this is a filter, and it's using negative values as well. So here's a filter which sort of looks similar to what we've already seen. This is now a 3 by 3 filter. Okay. Each one of these is 3 by 3. And as we had thought, over here, it's looking for a left-leaning line over here. This is looking for a right-leaning line over here. And what do you think this is doing? It's exactly, this is now a filter which is specifically looking for a cross. Okay, and it's very simple. It's got a bunch of ones. It's 3 by 3, and you can see that right there in the middle is the cross. Okay, so the plus ones are going to pick up plus values, and the minus one is sort of equivalent to the 0 that we had before. It's going to give out negative values. So if you look at the output over here, we apply this filter. The first filter, let's say this is filter number 1, F1, F2, F3. So this is filter number F1, this is F2, and this is F3. And let's just look at what happens when F1 is applied. Okay, so we're going to apply this, and we're going to keep sliding it over the entire image. Okay, and every time we slide it, the output goes to a different pixel, goes to a different point. Okay, so let's see what happens when we apply it over here. So this is a 3 by 3 filter which is just being applied to this image. And if you do the calculation over here, which is shown at the top, it comes out to be, 1 times 1, minus 1 times minus 1, minus 1 times minus 1. So you can see that all of the output is completely all ones. And so you get a very strong output, which is basically saying that there's a complete replica of the filter which is present over here. Okay, so there's a very strong message being sent over here that this is a 1. Now, if we look at applying the F1 filter over here at the X, now the X is not only has this slanting feature, but it also has this. Okay, so now we expect that the output should not be that strong. All right, and this is what you get. So if you apply this, just do the calculation. Sometimes you will get, so when you do a -1 with a 1 over here, you will get a negative value. Okay, and that's why when you see you have 1 plus 1 minus 1, and then a few minus ones, and because of this, the output comes out to be smaller. Okay, so here it's saying that yes, there's a 55% chance, you can say, that there is a left-leaning line over here, but it's not pure. Okay, there's some other stuff there going on. Okay, so similarly, if you apply it if you apply F1 to the complete output, what you'll see is some of these values are going to be very strong. Okay, which is basically saying that there's a very strong line over here in some of these places, but in the center there is some distortion over here, and in other places there's nothing there. It's very small. You can see it's only 0.11, which is basically saying that yes, there seems to be some line, but it's not really a left-leaning line. Okay, so this here is picked up, this filter here is picked up a very strong left-leaning line. Okay, now if you do this for all of these 3 filters, so this is F1, This is F2, this is selecting across. This is F3. Then what you see is that F2 in the center, when it's applied in the center, will pick a very strong value over here, a 1, because it finds that the center is exactly what the filter is looking for. Okay, and so if you can look at it, this is selected the left leaning line, this is selected the right leaning line, and this here is selected the X. Okay, so when you combine all of these, and then of course there is we also have max. You're also doing max pooling. Remember, we're doing max pooling. So max pooling, what it does in some of these cases is that it makes things simpler. It simply removes, well, actually, yeah. So it's doing max pooling with a stride of 2. So it's okay. So it's picking out, it's making the image smaller. Sometimes the images become too large and you want to make it smaller so that the processing time is reduced. Okay, you basically want to pick the maximum feature from that particular section of the image. So as you can see that you don't really need to have all of this. Okay, if you've got, for example, these two over here, all you want to see is that yes, there is a left leaning image in the top quadrant. Okay, so we can simplify that and we can use max pooling to simplify it. So it'll say that the maximum value over here is 1. Okay, in the next case, the maximum value over here is 0.3. So it will disregard the unimportant features. Basically, what this is saying is that I'm going to look at the important features in the image, and if those match, then that's good. Okay. So max pooling is basically, this is what it comes out to be. It's basically a smaller version of the original image, but you can see that it still has the important feature that it has the left leaning line over here, which is demonstrated over here, all the way up to here. Okay. Now, if you apply max pooling to all of this, you can see that the original image was fairly large. The output image is now almost half the size, and it's again similar to the original image. It's picked out these values over here. It's sort of slightly distorted, but it's picked out that there is a right leaning image line, there's a left leaning line, and there's also a very strong X present. Okay, so max pooling has been done. The next thing that you do is ReLU. Okay, now ReLU, what it does is simply makes the negative values go to 0. So there aren't any negative values in this particular example. So yeah, if you applied ReLU without the max pooling, then you can see that it would basically zero out some of these values. Okay. You know, it's not important at this stage to understand why ReLU is being used, but it's used to make the negative value 0. So if you stack the layers together, you do. Yeah, we're basically looking for positive values, positive numbers, and the negative numbers actually aren't adding too much value. So we just want to zero them out. Okay. So basically what it's saying is there's a very negative feature. This feature is definitely not present. Okay, that's what a negative value is saying. Well, let's just make it 0. Okay, 0 is basically saying the same thing. Yeah, so there's an importance of 0, as you know. So so the convolution layer is now being fed to the ReLU layer, which is being fed to the pooling layer. Okay, this is the normal order. So the ReLU layer basically removes all the negative values, and the pooling layer makes it smaller. Okay. So this is what you get as an output, and then you deep stack. Okay, so you've got this whole layer, this is going into the next layer, and so on, as you saw earlier. Okay, and at the end of it, if you've done you've done pooling twice. So if the image was originally large, it's going to eventually come out to be fairly small. So at the end of it, you only get a 2 by 2. Why? Because you've done pooling twice, and if the original image was, let's say, 8. Then you became 4, and then it became 2 by 2. Okay, I'm assuming that both of these pooling layers were 2 by 2 filters.
Is the output size the same as the filter size of the pooling layer?
Is the output of what? So let's just go back over here. So let's look at each one of these in turn. Okay, so of the convolution layer, the output size is approximately going to be the same. Okay, because you're doing a stride of 1. You're actually going 1, 1, 1, 1, and so on. Okay, so the output size is going to be approximately the same. The ReLU layer is also going to be exactly the same, because in the ReLU layer, we had the ReLU layer. You can see that the size is the same. Okay, the only thing which is being used to reduce is the max pooling. Okay, and if you use a max pooling of 2 by 2, it's going to make it half. If it's 3 by 3, it's going to make it 1/3. If it's n by n, it's going to be make it 1n, 1 upon n. Yeah. So so we used 2 pooling layers, so you can see that the output has become fairly small. So if you look at the output over here, it's basically saying that after all of this processing, this has found a strong left-leaning layer line. This has found a strong right-leaning line, and this has found an X. Okay, so basically, as a result of this, we are almost quite sure that this output is going to be an X. Okay, and if you go back to the starting point, what we had tried to do is, I don't know if I mentioned this, what we're basically trying to do is, when we feed it an X, we want the y1 value to be larger than the y2. Okay, this is what we were expecting. And now you can see that in this particular example, we are probably, as a result of this, we hopefully being able to get that y1 is going to be coming out to be a strong value after we've done the fully connected layer, which is not done yet. Let's go to the final layer. This is the fully connected layer now. So what we're saying now is, in the previous case, you had 2 by 2 times 3. So you have how many outputs? 4 times 3, 12 outputs. Okay, so these 12 outputs, 1, 2, and all the way down up till 12 over here, are now, each one of them is going to be connected to output number y1 as well as output number y2. So I haven't shown y2 yet, but as you can see that the output y1, this particular neuron, is going to be connected to each one of the inputs. Okay, after a lot of training, what are we going to expect? That again is going to have a strong weights associated with these two values. Okay, it's also going to have a strong weight associated with this value over here, which is basically selecting an X. But notice that it's going to have strong values with all of these. Okay, and this is going to have strong values over here, specifically with these two values. Okay, so that's why these links have been shown in bold, because they have stronger weights. Okay, that's how. Now, can you guess how an O would differ from this? Would O have the same weights associated with it, or would it be different? Clearly, it has to be different if it's doing classification. Okay. Yes, they're going to be constant. So there will actually be how many weights? So they're going to be 12 weights over here, 12 weights over here. There's going to be a total of 24 weights trained. So y2 weights will be different from y1 weights. Okay, remember that's what we said earlier as well. If you remember going back to this example, so we said that this is the same network. So you're going to have y2 is also going to be connected over here and connected over here. So the y1 weights are going to be strong over here. The y2 weights are going to be strong over here.
So in this case, for both images, the weight will be different, right?
No, the weights are going to be the same. After the training, after you've done all the training, the weights will be constant. The difference will be the image itself. The input will be different. So, okay, so when you're feeding it two different inputs, the outputs will be different. Okay, so in this case, in both of these examples, from here till here, these filters are the same. Okay, and these weights are the same. Okay, filters are the same, and the weights are going to be the same. Okay.
So on the last page, are these the weights of the bench?
So going over here to the X and O example.
Yes.
Yes. So these are now the weights. Okay. So, and of course, there are going to be filters as well, which I haven't, all of those other weights are going to be trained. But
if these are the weights,
yeah,
you just said that weight will be same.
Will be fixed, yes. So the weight, all of these weights, these 24 weights will be the same, but the weights associated with Y1 are going to be different from the weights associated with Y2. Okay, Y1 is going to be looking for certain features. Y2 will be looking for different features. So Y1 will be looking for the X's and those lines, and the Y2 will be looking for the vertical lines and the horizontal lines. Okay, so it's going to be connected differently. So here's the final output. So when you feed it an X, okay, what's going to happen is that this number is going to come out to be large. Why? Because it's picking out these values. Okay. In this example, the O value is going to be small because the O is picking out, is looking for these values. So you see the green lines over here? Those are the weights associated with O. And those are different. It's connected strongly with different features. The X is connected to this feature. O is connected to this feature. Okay. So when this is strong, it will say this is an X. When this number here is strong, it will say that this is an O. Okay. That whole series of numbers. Okay. That's what I mean. So when the numbers associated with these green lines are strong, it will say this is an O, more likely an O. When the numbers associated with those black lines are strong, it will say this is an X. Okay.
Just a question. For example, the first, this 0.9, will it also be connected to 0?
Yes, yes. So you can see there's a very light line over here. Can you see that? So this is basically it's saying that this weight over here will be very small. So this could be 0.1, okay? But this weight over here could be 0.9. Similarly, this weight over here could be 0.9, and the weight over here, for example, this weight over here, linking X with this number here, could be very small. It could be 0.2. Okay, so it's fully connected layer. Every input is connected to every output, but the weights are different. Okay, and those weights are actually basically deciding, and these numbers over here based on the input are going to finally decide what these output numbers are. Okay, so this was sort of the end of the convolutional neural network as such, and this explains the whole concept, right? Going right from the beginning till the end, how different images can be classified. Okay. And just going back over here, this was some more examples of layer 2. So you can see that, and again, this is drawn from this YouTube example. You can look at it later. You can see that if you've given different patterns over here, these are the different neurons. Okay, so each one of these is a neuron and the output of a neuron. Okay, and if you look at it, as I showed you earlier, some of these neurons are they're very simple. When you're feeding in this image, the output looks something like this. Okay, but different neurons will react differently. And this is layer 2, so you can see all of the features being selected are fairly simple. Okay, this is another example with layer 4 being shown. All right, and you can see that layer 4 has actually much higher level of features. So here you can actually see, I don't know if you can zoom in over here, but you can see that an entire the entire features of a bird is being selected by this one neuron. Okay, so when it sees that type of image, it will say, yes, I found, whatever this bird is called. So that's how neural networks and deep neural networks work. Okay, so now let's do a little bit of a review and see that in terms of the artificial neural networks that we've studied so far, we looked at basically two types of neural networks. We've looked at ANNs, and in ANNs, what was the basic difference between ANNs and CNNs? Remember when we first did an artificial neural network, we said that you have a bunch of neurons and they're connected to each other, and there's an output, and there's an activation layer over here, and there's a summation layer over here, and there are weights over here. Okay, and there's a output over here, and there's some kind of an activation over here. So that was your artificial neural network. Now, how was CNN different? So not only did you have inputs like this, and you had these weights. Now, what were these weights in a CNN? these weights were actually your convolutional filter. So this was basically how it was different. So what you were doing is basically when you take your you took your input, all right, you were applying these weights not simply by taking the weights and multiplying them, but you're applying an entire filter over here, and you would put the filter in this particular portion, then you would move the filter a little bit, and then you would move the filter at different places, and then you would get a whole series of output. So basically the algorithm was a little different. So each one of these weights actually in the convolutional neural network were actually corresponding to the weights in a filter. Okay. And the convolution or the filter operation was basically able to work on a 2x2 image. Okay. And that is basically how CNNs were different from an artificial neural network. So that's one thing that we've studied so far. Now the question is, what do you think ANNs and CNNs so far have been able to achieve, and what are the things that they have not been able to achieve? And if you look back at some of the problems that we studied, maybe in our initial all the way till our first lecture, and if you look at the different types of problems that we said existed, which one of these problems so far have been solved? So if you look at all of these problems, right? So we said that there are different types of AI problems. You've got expert systems, deep learning, computer vision. So maybe we've sort of looked at computer vision so far. Okay, we focused in on computer vision. We haven't looked really at natural language processing. Okay, what do you think is different between natural language processing and computer vision? Can you think of one major difference between these two?
Sir, you mentioned about the Chinese problem. So
Yeah.
Basically what we're trying to do is try to solve a problem. You're basically unable to get the syntax, the semantics of it. We get the syntax.
Okay. Yeah. But in terms of the actual data, what's the basic difference between, let's say, a computer vision data versus somebody who's speaking? And think about stochastic networks for a little while. Remember, in stochastic networks, we said that you have an X, and but what did X also have? X also had a T in it, right? So it was a process over time, and there was some relationship between, for example, if you're looking at the stock exchange, right? There was some relationship between the stock value today and what it was yesterday as well. A lot of times it doesn't look like it, but there is some relationship, right? If the stock market is at 40,000 today, then yesterday it couldn't have been at 10,000, right? It may have been at 39. So there's some relationship. Similarly, when you're speaking, is there hopefully again some relationship between what I'm saying in a sentence, the relationship between the words? There is, right? So a lot of times there's a time element which is linking the data. Okay, but in image right now, so far, have we said that there is any relationship, there's any time element involved? So far we haven't looked at that. We're looking at still images. Okay, but can you have images in time as well? Yes, what is that called? It's called video, right? Basically, it's a series of images which are taken over time. Okay, and now is there a relationship between an image which was taken 25 milliseconds ago and the next image in the frame, which is 25 milliseconds later, or let's say a second later, and so on, in a video? Yes, there is, right? Because if I take an image of you guys, you're all pretty static, but there's slight movement of the heads and hands and so on. So if I was able to detect that there were 3 persons in this room right now, and I gave it an image 1 second later, do you think there will be 2 persons, or there will be 3 elephants, or 2 horses? Hopefully not, right? There will. The class is full, but hopefully there will most likely be 3 students again. Okay, because the images will not be very different. So there is a strong linkage between over time. Okay, and that's something we haven't studied so far. That's one of the differences that we haven't looked at so far. So let's keep on looking that.
Sir, you also studied this in environments when some environments are static, if you remember,
Yeah.
but they are fully observable.
Yes.
The images are fully observable.
Right.
But when we have a text, it might have meaning beyond it.
It might have meaning beyond.
But like sir, for example, if we have a page, let's suppose we have lots of sentences, there might be even sentences which are sarcastic or they don't have the original meaning.
Right, right, right.
This is also different.
Yeah. So that becomes a little tricky as well, to be able to get the meaning out of a sentence, whether it's a sarcastic meaning or it's a negative meaning, because you may have certain words. I may say you're good, but I'm saying you're not that good, right? It still has good in it, but I said before that, okay, or before that I said not. So that sort of completely changes the meaning of the word, okay? And sometimes, a lot of times in sarcasm, you're saying something and you meaning completely opposite. Okay, you're really good. Like,
Because for data, it is your good. Like
yeah.
I'm good.
So if I'm saying, oh, you're really good, right? So I'm sort of saying that in a sarcastic way. So that becomes a much more difficult problem, and we're not at that stage yet. Okay, in this particular course, we're not addressing that. So we again taking step by steps. So what are the things that we have? If you look at some of these examples that we were trying to classify persons, do you think now we're able to classify these images? Have we gotten to the stage where we can classify an X and an O? Now, can we classify between person X and person Y, or classify between a duck and an ostrich or a car? All we need to do is make it more complex, right? Make it deeper networks, and we need to do more and more training. But conceptually, we've now learned how to do that. All we need is a convolutional neural network, which is large enough. And if it can detect a spiral, it can also differentiate between different types of creatures, okay?
Is it possible that we don't have to define the filters?
Yes, so we're not defining the filters, right? So far, all I've said is that you give it enough images and the filters will automatically be designed. Okay, and that's what we saw in the neural playground as well, that we weren't actually designing the filters. Okay, but the TensorFlow did not really take CNN. It wasn't using CNN. Okay, it wasn't really applying. Otherwise, it would work much better. But if I have time, well, I don't have time today. But in the next class, what I will show you is an example of how CNN is applied to real images. Okay. So far we've gone over some of these things. We haven't looked at recommendation engines. We'll hopefully look at that. Picture captioning is again a difficult problem. We haven't looked at that, but we have looked at some of these problems. Okay, so let's get back to our current lecture and see where we are. Okay, so many of the problems haven't been solved. One of the problems, as I said, is that we're not looking at time yet. So we have to look at time. So that's one of the things we look at next. Another problem that you can think of is the following problem. And this is what is also referred to as a Picasso image problem. Okay, I don't know if you're familiar with the Picasso painter. He used to draw some of these arts which had absolutely, the images are kind of distorted. So if you look at this image, the left image, which is a proper face, and the right image, which has all the ingredients which were present in the left image. It has the lips, the eyes, the left eye, the right eye, the mouth, maybe the nose is missing. No, the nose is also there. So everything is there, except they are not in the right order. Okay. So the question is, what do you think the CNN will tell you? When you're looking at the output over here, what is it? Is it really looking at the sequence of these features? It's basically looking at this feature over here would be saying that, is there a nose present? This might be associated with, lips. But is it really saying that, can it really differentiate between these two images, do you think, in CNN? It might be able to say, well, if the eyes, for example, are identical, so this eye over here is identical to the other eye, and this eye is identical to this, for example, the mouths are identical, the nose is identical. So if you gave both of these images to the CNN, the convolutional neural network, let's say this gives you a probability of 0.95 that there is a face. What do you think this output will look like? Will it be 0.95 or it will be 0.05? Which one is more likely?
0.95, sir, because it's
Somebody online is saying 0.95. So the reason, and that's the right answer, the reason why it will not be able to differentiate between these two, because it doesn't know, has no information about the position. All it's able to say is that yes, an X is occurring, but it doesn't really know where. Okay.
it is sensing all of the features, but it is not basically.
It's looking at the features, looking at the presence of the features, but it's not really looking at the relationships of those features. Okay. So if, for example, if I gave you another picture, and this picture was the same picture, but it was, in this corner. Okay, so you had a nose and a face over here, or there was another picture where the face was over here. Okay, and there's another picture where the face was in the middle. Now, in all of these cases, it would detect that a face is present. Okay. But it won't really say that it's in the left corner or the right corner, or if the face is upside down and so on, or if the images have been distorted. So can one think of a way to be able to solve this problem? Because clearly I don't want this 95% probability that there's a face, because unless there's an alien present on this earth, this is not a face. Okay. I want this to be able to say that yes, there is a face, but I want this to be able to say that, maybe there's 50%, yes, all the features are present, but it's not really looking like a human face. Okay. So how can we change CNN or neural networks to be able to differentiate, to be able to actually find relationships between the positions of those features? So you want to be able to say that the nose and the mouth and the eyes should be in a specific order, right? It should be sort of like this: nose in the middle and the two eyes and the mouth. Okay. So can you think of, based on all the information that you already have, all the courses that you might have studied, some math courses, can you figure out some way that you could actually define relationships between these features, which doesn't seem to be present in CNN? Yeah.
So
Vector.
you could have a sort of mask. So suppose you know that the eyes are supposed to be in a certain position. So you could have a certain mask where you know that the value of the eye should be mapped to a certain place in the mask. So
okay,
they will multiply. If it's out of the place that it's supposed to be, the value will become 0. But if it's in the mask, it will give a high value.
Okay, very good. So what you're saying is that we could have a mask which is somehow, this is the kind of mask I'm looking for, right? So it's basically saying that this mask is not only looking for the features, but it's looking for some relationships between those features as well. So in a sense, partly we have addressed this problem by, if you look at this example over here, where did it disappear? Right there at the end. So if you look at what we've done over here, I think it was right at the beginning. Yeah, so basically the mask that you're referring to is sort of like a deeper layer, which is now saying that not only am I looking for eyes, but now I'm looking for the entire combination of the face. So yes, that's partly addressed, but now let me rephrase my question. What I should have actually said, which I'm saying now, is that I'm also looking for if this face is lying on the side. Okay, so the eyes are like this, the nose is like this, and the mouth is like this. Now, is this a face? The person is lying on the ground. So yes, I do want to be able to say that there's a 95% chance that there is a face, right? But now what's happened is that all of these features are actually in a different position. Okay, they all have been rotated by a certain angle. Now, so these two are sort of related things. And you mentioned over here that what we could do is have vectors. And what we could have is vectors sort of indicating how the nose and the eyes are related to each other. Okay, and also the mask concept. So both of these can be sort of combined together. So these are both great ideas, but now we've gone beyond our time. So we'll stop over here and we'll see how these can be solved. And one of the techniques that is done is called, well, I'll just tell you what it's called. Those are called capsule networks. Okay, and that's something very recent. It's a cutting edge technology. In fact, one of my PhD students is now working on it. And it's recently been proposed by Jeffrey Hinton, which is one of the original gurus of deep neural networks. And we're having good success in it. Okay, so we'll talk about capsule networks in the next lecture and other techniques as well. Okay, to be able to address time issues.